This module is about assessment of sustainable energy system. In this module, we will learn how to assess an energy system from the viewpoint of sustainability and where we can improve the performance of energy system. Among various energy systems, which one is more sustainable, we can assess it both qualitatively and quantitatively. The term sustainable energy is originated from term of sustainable development and it is similar to the criteria of sustainable development. Sustainable development is based on three pillars, that is social, economic and environment. A development will be sustainable one if these three criteria be fulfilled. From the figure, we can say sustainability is the intersection set of these three. Similarly, for energy system, sustainability is measured with social, economic and environmental dimensions. From economic dimensions, cost effectiveness of the system, self-sufficiency and availability of financing are measured for successful operation of energy system. Greenhouse gas emission, depletion of natural resources and toxicity on human and ecosystem should be within the specified limit. For successful deployment of energy system, it should be acceptable socially also. Employment, land issues, food security and impact on communities of the energy system should be taken into the sustainability study from the social point of view. In this lecture module, we will try to assess energy systems through thermodynamic, economic and environmental viewpoint. Thermodynamic assessment is done with energetic and exergetic point of view through first law and second law of thermodynamics. If exergy efficiency be higher, then utilization of natural resources will also be higher. Sometimes thermodynamic, economic and environmental assessments are interdependent. For example, better thermodynamic performance leads to lesser depletion of natural resources and it is reflected on economic benefits also, and better the environment is achievable. Sometimes sustainability of energy system is directly measured by exergetic performance. For example, sustainability index, which is inversely proportional to exergy destruction, is used as sustainability parameter in some cases. Environmental assessment is done through life cycle analysis. Sometimes systems are optimized based on combined thermodynamic, economic and environmental parameters. Say exergo-economics or exergo-environmental analysis is used for this purpose. Finally, system should be socially acceptable also. Thermodynamic assessment of energy system is done through first law and second law of thermodynamics, that is by calculating the energetic and exergetic efficiency. From the lecture module of polygeneration, we know that there may be multiple input or multiple output of an energy system. Energetic efficiency is defined as the ratio of energy equivalent of all utility outputs to all kind of energy input. Energy input may be in form of fuel energy or in form of energy of steam. Similarly, exergy efficiency, sometimes it is called energy utilization efficiency, is the ratio of exergy of output utilities to the exergy of input utilities. Then question comes into mind, what the exergy is? Why study exergy? At first, let us know why we study exergy. Exergy is a thermodynamic property of a system with respect to environment. Exergy analysis had been used for system optimization and performance evaluation in last several decades. Better is the exergy efficiency of a system, better will be the economic payback. That means if exergy efficiency is higher, then utilization of natural resources will also be greater. By analyzing amount of exergy destruction in a equipment or within a process, we can see where we should focus our efforts to improve system efficiency and to utilize maximum of natural resources. It can also be used to compare various processes or systems and helps to take decision regarding design parameters of any thermodynamic processes. Now the question is, what exergy is? Conceptualization of exergy is important. Let's consider a body at temperature Ti placed in contact with the atmosphere at temperature T0. If Ti is greater than T0, that means if the body is hotter than surroundings, then the body cools spontaneously until it is in thermal equilibrium with the atmosphere. That means body rejects an amount of heat to surroundings, that is Q, until its temperature becomes T0. However, by controlling the cooling, work can be developed as shown in next picture. Instead of cooling spontaneously, if the heat transfer Q passes through a power cycle that develops work W, that is, place a heat engine in which Q is the amount of heat input. Then heat engine will develop an amount of work by this heat input. The developed work is fully available for lifting a weight, developing shaft work or generating electricity. Thus, any system or body which is at different state or different composition from surroundings has the ability to do some useful work. For example, natural gas has different chemical substances with respect to surrounding air. When combustion takes place in natural gas, it generates heat. This generated heat has ability to do some useful work. That means natural gas has some exergy value. Similarly, other thermodynamic or chemical systems may also have work potential. Let's define exergy formally. Exergy is also called as availability or work potential and may be defined as the maximum useful work that can be obtained from a system at a given state in a given environment. In other words, the most work you can get out of a system. Thus, exergy is the property that quantifies the potential work for use from a system in a particular environment. In this definition, there is a term called environment, and exergy or work potential depends on this environment. Then question comes, what environment is? Environment is the area of surroundings which is not affected by the process at any point. For example, if you have a hot turbine, the air adjacent to the turbine is warm, the environment is the area of surroundings far enough away where the temperature is not affected by the turbine. Another pillar of sustainable energy system is economics. An energy system should be economically feasible and beneficial for its successful deployment and for long-run operation. The economics of the plant is tested by requirement of capital investment and profitability criteria. Let's first find how to calculate capital investment. Total capital investment, that is TCI, consists of fixed capital investment and working capital investment as given in equation 1. During capital cost estimation, if data regarding fixed capital investment is available for different capacity, it is normalized by equation 2 using capacity ratio and its exponent x. Time value of capital cost is normalized according to equation 3 using cost index, say chemical plant cost index or CPI value. This index is changed according to time value of money for chemical plants. Within that time, depreciation of plants occur. Three kinds of depreciation method can be used to calculate annual cash flow. This helps to estimate net present value or NPV of the plant. However, there are two types of cost associated with a plant. One is capital cost and another is variable operating cost. Variable operating cost depends on the production size, say fuel cost, labor cost or cost of chemicals, etc. Let's show two applications of process economics. Break-even analysis is shown in figure 1. The break-even analysis helps to estimate the minimum production rate so that total income and total production cost become equal. This condition of no loss, this is the condition of no loss, no profit. This point, the point at which it occurs is called break-even point as shown in the figure. However, total production cost consists of fixed charges and variable operating cost, which is a function of production rate. Example of fixed charges is equipment cost and variable charges may be fuel cost and labor cost. Plant capacity should be more than the break-even production rate with a margin. Economic analysis also helps to optimize the size of plant. In figure 2, an example is shown to find the optimum plant size for a biomass-based hydrogen production system. The plant size is optimized by minimizing the selling price of hydrogen, even taking the transportation cost of biomass. Hence, process economics is an important tool for applications for sustainable energy system. Profitability criteria of a plant is determined without or with time value of money. Return on investment or ROI and payback period or PVP are used as profitability criteria as shown in first two equations, where TCI is total capital investment and FCI is fixed capital investment. Net present value or NPV, IRR, DPBP are used as profitability criteria by taking the time value of money. In the figure, discounted cash flow diagram of a polygeneration energy system is shown. From the figure, we conclude that in the first 3 years, slope is negative due to capital investment for construction of the plant. Then the slope becomes positive during operation of the plant and revenue generation. After 9 years, cumulative discounted cash flow becomes positive. Hence, discounted payback period is above 9 years and NPV after 13 years is $100 million US. Another important pillar of sustainable development is environment. In this lecture, we will learn how environmentally sustainable products and activities can be identified using life cycle assessment as a tool. Sometimes LCA is called as life cycle analysis also. Then question comes into mind, what is life cycle? Life cycle is a consecutive and interlinked stages of product or processes from raw material acquisition or generation from natural resources to final disposal. LCA is a technique to assess the environmental aspects and potential impacts associated with a product or process. There are few steps in LCA. First, compiling an inventory of relevant inputs and outputs of a product system. Then, evaluating the potential environmental impacts associated with those inputs and outputs. Then, interpreting the results of inventory analysis and impact assessment phases in relation to the objective of the study. LCA studies about the environmental aspects and potential impacts throughout a product's life, that is from cradle to grave, from raw material acquisition to production, use and disposal. The general categories of environmental impacts needing consideration for energy system include resource use, human health and ecological consequences. An example of LCA study of a polygeneration system is shown in next figure. The figure shows a polygeneration fueled by waste of crop production, that is rice straw. From cradle, that is from nature, material is extracted and processed for equipment manufacturing. These equipments are used to construct the plant. During these processes, environment is polluted in several ways. Then environmental impact of each step is evaluated and the life cycle inventory data is made. Similarly, straw baling, storage and transportation are included in the LCA study. During operation of the plant, chemicals are also required. A system boundary is indicated as shown in the figure. For different LCA cases, the assumptions, data and system boundaries may be different according to goal and scope of the study. Hence, it is important that this should be defined in accordance with goal and scope of the study. In full LCA studies, the system boundary is drawn to encompass all stages in the life cycle from extraction of raw materials to the final disposal, that is from cradle to grave. The scope of such studies can be from cradle to gate also, as they follow a product from the extraction of raw materials to the factory gate, not to the disposal. During this journey of cradle to grave or cradle to gate, it produces several harmful impacts on environment. Goal of the LCA study is to find those impacts during this journey. LCA can be made for products or processes. A few important terms and definitions are used in life cycle analysis according to ISO 14044-2006. The terms are life cycle assessment, life cycle inventory, life cycle impact assessment, life cycle interpretation, etc. The definitions are given in study material. Study of LCA varies on objectives, place, time, etc. Hence, there is a framework of International Organization for Standardization, that is ISO, regarding LCA. This international standard specifies requirements and provides guidelines for life cycle assessment, including the goal and scope definition of the LCA, the life cycle inventory analysis phase, the life cycle impact assessment phase, the life cycle interpretation phase, reporting and critical review of LCA, limitations of the LCA, relationship between the LCA phases. This international standard covers life cycle assessment for LCA studies and life cycle inventory or LCI studies. The intended application of LCA or LCI results in considered during the goal and scope definition, but the application itself is outside the scope of this international standard. This international standard is not intended for contractual or regulatory purposes or registration and certification. Impact categories are the parameters through which we assess any products or systems. The selection of impact categories, category indicators and LCIA models must be consistent with the goal and scope of the LCA study and must reflect the environmental issues of the system under study. Hence, selection of impact categories is important. It should cover various environmental aspects. There are two types of method to assess environmental impact. One is problem oriented and another is damage oriented. In the problem oriented methods, the environmental burdens are aggregated according to their relative contribution to the environmental effects that they might cause. They are often called as midpoint approaches because they link the environmental interventions from life cycle inventory somewhere in between the point of intervention. Damage oriented methods model the endpoint damage caused by environmental interventions to areas of protection, which include human health, damage to ecosystem, or destruction of natural resources. Sometimes these effects are expressed in a single score by normalization. Midpoint indicators, different environmental impact categories are expressed in different equivalent units according to their damage potentials. Let's give an example. Climate change or global warming is caused by carbon dioxide, methane, CFCs and many other substances. Amount of these substances are converted to equivalent amount of carbon dioxide. Hence, global warming potential is expressed in terms of kg of CO2 equivalent. An example of midpoint indicators is CML method, which was developed by University of Leiden, Netherlands. In CML2 method, environmental burdens are aggregated according to their relative contributions to the environmental problem or impact that they potentially cause. Environmental impact categories, its abbreviations and units of CML baseline is shown in the table. As they are quantified at the intermediate position between the point of environmental intervention and the damage caused, the impacts calculated by this method are categorized as potential rather than actual. Thus, if an energy system is assessed through economic, environmental and social viewpoint, we can measure the sustainability of energy system. However, these viewpoints are ever changing. Inclusion of new technology or new findings may change the dimension of sustainability. Hence, time frame of sustainability should be taken into account. Assessment of sustainable energy helps to tell which direction we should go for better future. Sustainability assessment is a scientific foundation for taking sound decision for sustainable future. Thank you.